Okay, so one of the major challenges associated with the Cox-Ross-Rubinstein model is the extent to which how much computational cost is involved in running a Cox-Ross-Rubinstein binomial tree. There are different ways of dealing with that. Two very interesting approaches were put forward by Kim and Wynne 1994 and then Curran 1995, and those approaches relied on being able to detect the early exercise boundary, right? So being able to find the early exercise or the optimal exercise boundary efficiently could increase the speed of estimation. The problem that both Kim and Wynne had, and with Curran subsequently, was how to handle dividends. And Kim and Wynne just took the view that you accelerate acceleration of the lattice but just ignore dividends, and they found that the estimation speed increased by 2 orders of magnitude. Curran likewise followed on from Kim and Wynne. He also had that difficulty, but he allowed for dividends. In the case of the call option, he allowed for dividends where dividends didn't exceed the value of the risk-free rate. But still, many situations that arise, particularly in the current environment where interest rates are very low, dividends will exceed the risk-free rate, and call options then become problematic in terms of valuation. So I think these were big improvements introduced by both authors. The downside was that they had restrictions around dividends. And what we do in this paper, which is set up on the SSRN network, is to speed up, to extend these two approaches and to take the runtime estimation, the computational runtime for a particular type of lattice, static, so very slow. We take deliberately 2 snippets of code that we put in the appendix to this paper, and in the estimation that we perform, we demonstrate that you can take the runtime speed from 18 minutes down to 3 seconds. Now, we take the slowest code that we have, but code that's very standard in many instances, kind of textbook code, in VBA, Excel VBA, and we note that the estimation time tends to be high depending on machine, but it is going to be high, and then we can reduce that fairly dramatically in terms of the runtime estimation. Okay, so where do you find this code? Well, if you download, if you download the paper and you come to the appendix in the paper, then the snippets of code are available here at the end in the last couple of pages. And we take the code from Fabrice Roy. This first snippet, which is for a static model, we take this code from Fabrice Roy. He posted CRR code on his website, on his portal, and also we take code, then we develop our own code as well that makes use of this idea that we can trace out quickly the optimal exercise boundary. Our big contribution here in terms of the literature is that we get the speed both Kim and Wynne and Curran then subsequently managed to obtain, but we do it without the restrictions being placed on the dividend. And again, the improvement in estimation time can be viewed as being relatively dramatic, in that if we take a 15,000 step tree, we can take the estimation time down from 18 minutes to 3 seconds. Okay, so what I've done here then is I've set up a little experiment. I've 2 snippets of code, and one where I've set out this static type code, and we can look at the estimation time. Now I know the true value here, this is an American option, so I'm looking at the value of American options for with a call specification. And there is slow code, and then there's the faster code that we've developed in order to take advantage of this efficient lattice search. And also to we borrowed the idea from Curran, who published in the Journal of Derivatives in 1995, and also his paper is based on a previous paper, or develops a previous paper from Kim and Kim's Buin and Kim. Okay, so this paper, Kim and Buin 1994, which is this other paper, and they basically explained that that the purpose of this paper, so this is the Kim Buin paper 1994, purpose of this paper is to improve our understanding of the behavior of the optimal exercise boundary in the binomial model. This enables us to develop an efficient recursive valuation method which incorporates the properties of an optimal exercise boundary. It is shown that this valuation method is as simple and as computationally more efficient than the conventional binomial model. What they leave out here is dividends. So the Kim and Buin paper excludes the possibility of dividends. Curran then subsequently follows in the Journal of Derivatives 1995, again that's an old paper as well, and extends the Kim and Buin results by incorporating in dividends. But for instance, in the case of call options, there are some arbitrary, so the first applies arbitrary restrictions here. The first applies to arbitrary continuous dividends, while the second applies to R. So R must be greater than Y for puts, and R must be less than Y for call options. Otherwise, the Curran paper, the Curran model doesn't work. But again, the idea here is accelerating the pricing of American options in binomial lattice in a Black-Scholes environment. The backwards standard induction method for solving an option valuation problem involves computation at every node of the binomial price tree. We show that many intermediate calculations are actually unnecessary, and eliminating them leads to a dramatic increase in computational efficiency. Test cases demonstrates that valuing an American put option can be accelerated by at least an order of magnitude while yielding the identical estimate of the standard Cox-Ross-Rubinstein tree. Now, what we do in our paper is, to go back to our paper, the efficient lattice search algorithm, we extend Kim Buin 1994, Curran 1995, and we allow for the inclusion of dividends. There's no restrictions on dividends. To set that up, then I have a couple of pieces of code here, and I might just explain. There are two sets of code at the end of our paper, just to go back. There is code for a static model, which is taken from Fabrice Rouat's website and book, and which is kind of a textbook. And then the other snippet of code is what we have developed based on our insights around an efficient lattice or an efficient search routine that identifies very efficiently the location of the exercise boundary, the optimal exercise boundary. Okay, so just to compare the two models side by side, with the efficient lattice, okay, we'll go with the Cox-Ross-Rubinstein model. Now, with these parameter inputs, the option actually is European, although we've designated as being American. And if we increase the up to 300, the true value here should be 1045 using Black-Scholes model. And these parameter inputs, note the parameters they're American. The option is a call. American, spot price 100, exercise 100, maturity 1 year, risk-free rate 5%, cost of carry 5%, so it implies dividend is 0. So B is equal to R negative Q, and the volatility is 20%. Entering those parameters, we should get a value closer to 1045. Okay, and we might note that as we increase the number of steps here, I'll go to 800. The Cox-Ross-Rubinstein result using the static code being where we don't use dynamic memory and there's no truncation, we get close to this 1045. Now I can also, there's a timer in here, so if I just highlight both cells together and then hit shift, so basically highlight both cells together and then shift control enter, right, we get the amount of time, so basically around 3 seconds estimation time, whereas if I use the efficient lattice search, again extending the array output, virtually no time at all. If we go up to 800, okay, it's much less. If we go to let's say 5000, the time taken is less than half a second. If I go to 10,000, the time taken will take more than double, 2.36 and 15,000 steps. And we probably are going to exceed here the 3 seconds. We get 6 seconds. Now this computer is a little bit different to the one that I used on the other